My name is Rebecca Fitzgerald.
And I'm Maria Crispin.
Thank you so much for coming this evening to join in our conversation. It's going to be very much a conversation between Maria and myself, and we really hope we'll have some good questions and chance to open up the conversation at the end. So I thought I would just start by a little bit of introduction about the Early Cancer Institute, where we're based, why we think this is an important topic, and then we'll get into the meat of our discussion. So you can see the staff of the Early Cancer Institute, scientists and staff at our retreat last year. And this is where we are on the biomedical campus, which you'll know is just a burgeoning campus of the hospital, research departments, industry, and biotech. And I hope you can see that green arrow pointing to the Early Cancer Institute. Our institute is undergoing a major refurbishment at the moment, which we're very excited about. And this will really bring our facilities up to scratch. And you can also see that I've marked there the Cambridge Cancer Research Hospital. So this is one of the government's new hospitals that have been announced in January. And what we're particularly excited about is that within this hospital on the top floor, so it will have the best view, is an early detection and prevention facility. So I think that really gives you a hint about the direction of travel for cancer care, that it's not just about looking after patients when they're unwell, but also being proactive and trying to think about how we can find cancer earlier and do things to prevent it from developing and becoming serious. So this is a graph which tells you kind of where we are and that we're not achieving what we had hoped. So you may be aware that the government set out a plan to try and improve earlier diagnosis of cancer. So cancer is usually what we call given a stage. And that's true of pretty much all cancers, certainly solid tumours. And stage 1 and 2 mean that it's diagnosed reasonably early, and it's still usually confined to the organ in which it started. Whereas stage 3 and 4 is more advanced when it's starting to spread to adjacent structures, and often also spread into the blood and the lymph system. So what we want to do is to be diagnosing more cancers at stage 1 and 2 than 3 and 4. So at the moment, the rough proportion presenting at stage 1 is about half, and the government set out to improve that from 50% to 75% by the year 2029, if I remember correctly. And what you can see on this graph is the blue line is our current status, and the pink line is where we wanted to be. So you can see that, this isn't good enough. So with the current kind of strategies that we have for earlier cancer detection, we're not going to make much progress unless we can do something innovative and different. And we think there is hope, and that's what we're here to discuss. And of course, when cancer is diagnosed late, it has a terrible toll on the individual and their family, but it also has a big economic toll on our health service, and it means that we're even more, and our economy in general, and it means that our resources are very stretched, and this also has impact beyond cancer to other types of healthcare, and these numbers are quite striking. So it's estimated that the economic costs of cancer, this is between 2020 and 2050, will cost the world economy $25.2 million. This is in dollars, which is equivalent to an annual tax, I'm going to read this here, of 0.55% on global GDP. So these numbers are pretty scary numbers. Okay. So what's our vision in the Early Cancer Institute? How do we think we should be progressing for cancer? And we think there are 3 key things. We need to predict who is at risk. So we don't want to turn into a society where we're all frightened all the time, and we're not enjoying our lives and living our lives to the full, and most of us want to forget about health. But we need to predict who amongst us are at risk and what we're at risk of, so that then we can tailor any early detection or screening strategies to the people who need them, for the right kind of test to the right person, and not waste time and resources for people at very low risk. So if you think, for example, our breast cancer screening, for example, is pretty much one size fits all. You have to be female, obviously. Men can get breast cancer, but very, very low risk, therefore we don't screen men. And it's an age-based decision when to screen women. But we know that not all women are at equal risk by any means. And some women may need one screen in their lifetime, or maybe no screening at all. Other women need heightened screening, and they need a different type of screening. They might need MRI rather than a mammogram if the breast density is high. So we know we can tailor, and the more we understand about cancer, then we can tailor how we predict risk. The second thing is about detection. So how do we find these early cancers and even pre-cancers? And then, of course, there's no point finding something if you can't do something about it. So, you know, pancreas cancer is one of the most deadly cancers, and it's very difficult currently to do something about it. So if you find something early, the treatment you have to have is still pretty full on, and has a lot of side effects and consequences and a mortality rate. So it would be great if we understood more about how pancreas cancer develops, and we could actually then come in and prevent it developing with some kind of medicine. That would be brilliant. So we think our 3 watchwords of the Early Cancer Institute are predict, detect, and prevent. So I hope that gives you a little bit of an overview of why we think this is an important topic. So I think now we're going to move into the discussion.
Conversation. Given that it's going to be a conversation, I thought I would start by asking you a question, Rebecca, if that's okay.
I think so.
I mean, you've dedicated much of your career to early cancer detection. When we talk about early cancer, what does that mean to you? Why is it so important?
I mean, maybe I can tell you a bit of a story about how I got into this. So I was a junior doctor in Addenbrooke's on a ward round, the kind of ward round we had in the old days with a huge number of doctors all peering at the patient. And there was this poor patient who had a cancer of the esophagus that was quite an advanced cancer. And the professor running the ward round was busy explaining to us that actually this cancer started from a pre-cancer called Barts esophagus. And that in this patient, when they'd done the examination with the endoscopy to visualize the esophagus, they could see the tumor and they could see the pre-cancer Barrett's lesion around the tumor. So I said, well, didn't she know then that there was the pre-cancer there? Oh no, that's not usually diagnosed. And that really stuck with me as kind of extraordinary, that here was a situation we knew what the precursor was, but usually that wasn't detected. And the other thing that really I think we've learnt more and more about, and is still kind of extraordinary, is the length of time it takes for a cancer to develop. So I explained about stage 1 and 2 versus 3 and 4, but actually to my mind we want to be going even earlier than stage 1 often to pre-cancer, because that pre-cancer, like this Barrett's, but for many other cancers, actually evolves over years. And it's estimated that the average tumour takes about 10 years from the time it was a pre-cancer to the time it's a full-blown cancer that's causing symptoms. So that gives both a challenge and an opportunity, because if there's that long lag period, then we can surely work out doing something about it.
I think we've got some slides here that show some of that evolution that you're talking about.
I've got the slides, so thank you. So here's the Barrett's example. So you can see on the top, these are pictures looking down an endoscope towards the stomach. And on the far left is a normal, healthy esophagus, which looks very light pink. And as you move along, you've got the dark pink moving up the esophagus. This is from acid that's damaged the esophagus, so that's the Barrett's lesion. And that can gradually turn to cancer, and that's estimated to take, as I say, up to 10 years. Now, it's challenging, of course, because if we start finding things really, really early, the next question you might ask me is, will they all turn into cancer? And they won't, right? So here we've got the great opportunity, because we can find these things early and try and track them and try and predict who's at real risk. But on the other hand, we also want to know the ones we don't need to worry about.
Yeah.
Have you got, was there a slide about the blood?
Yes.
Before this one, I think, yeah. So this is some research that's been done by one of our scientists at the Early Cancer Institute, Jamie Blundell and Caroline Watson. And this is a study about leukemia, a type called acute myeloid leukemia. And here they took bloods or they used bloods that had been taken from a very large population study, actually about ovarian cancer. And these patients had bloods taken every year. And some of them developed leukemia. And so they worked out how far back in time they could have spotted the very early leukemia changes. This is looking for DNA changes in the blood. And these lines going up are abnormal on that graph. And in some of these women, you could find the early signs of leukemia 10 years plus before they then eventually develop symptoms. And then this leukemia, once you have symptoms, often that's quite quick to progress. So again, there's this window of opportunity. So how do we measure it? And at what point would we then act to do something about it? So I think that's what kind of spurred me on. So this is the kind of technology we're developing. But Maria, I think it's my turn to put you on the hot seat now. So, you know, we need technologies for early detection. And some of these are evolving really quickly, like AI. And that's your specialty, and it's become quite a hot topic in society at large and in healthcare. Can you just tell us a little bit about, from your perspective, what do we actually mean by AI?
Yeah, I'm glad you're asking that question, because it's moving so fast that even for me, it's sometimes hard to catch up. Following your example, I'm going to tell you a little bit about where I come from. I'm actually a particle physicist by training. I did my PhD at CERN. I was looking for new particles that could explain dark matter. So absolutely not related to anything we're going to talk about today. And it was a fascinating time to be doing particle physics. Some of you may remember it was around the time when the Higgs boson was discovered, so it was all over the news. So I absolutely loved it, had a great time. And as you can imagine, in these types of experiments, there's loads of data being generated. We had loads of collisions, and we were analyzing these complex images, looking for very, very subtle patterns that could tell us what some of those particles were. And towards the end of my PhD, when I was starting to think about what I was going to do next, I found a few papers about how some of these ideas that we called machine learning back then, that the term also evolves over time, the fancy term is AI now, could really make a difference in medicine, and in particular in the cancer field. And I thought, well, this would be a great opportunity. And I actually have to say it was Cambridge, the university, that gave me the opportunity to just explore a new field. And so I started working in the advanced cancer field, simply because there's more data in that space. And slowly I realized that the really big opportunity is in the early cancer subfield within cancer. And the reason why AI can make a difference is that, and here comes the definition, AI is a computational tool that can learn from data and can make predictions without you having to specifically tell it what to do. And this is important because we've had computational tools for a long time, but they were based on rules. We had preconceptions of what they were supposed to do, and that meant that they were useful, but limited in terms of their abilities. And the idea behind machine learning is that you've got these complex algorithms that are tunable, and the data that you show them is what tunes them effectively. And we've seen a really exciting evolution in machine learning in the past, I would say, 20 years or so. In the 2000s, we were talking about algorithms that learn from data, and that was already really exciting. That was the big revolution in machine learning. Then we started talking about deep learning, and these were algorithms that were able to learn from even bigger data sets and learn some even more subtle patterns in the data. And the reason that AI is becoming so important now, again, is that we're in some kind of new era that is characterized by these foundation models. And what is a foundation model? I mean, I'm sure that most of you have heard of ChatGPT or have played around with it. These are models that have seen vast amounts of data, like nothing we've seen before in terms of the quantities. And they've learned about the intrinsic patterns in that data. So ChatGPT has seen loads of text. It may not be the text that you're interested in, but it's seen so much of it that it's learned to recognize the right patterns in the data. And so you can then show it anything else, you can ask anything else, and it will have enough prior information to be able to give you something useful. And this is why AI as a technology is also so exciting for us in early cancer research, because it's now enabling us to ask questions and to focus on some really unexplored areas, simply because, well, as you were saying earlier, we hadn't thought about it before. Maybe we don't have the biggest data sets, but now these tools can give us the opportunity to ask questions, to predict, to hopefully prevent in the future.
Data's the key, right? So
and data is absolutely the key.
What we need to do more is make sure we have the data.
Yeah.
We might get onto this later, and the rights to use the data so we can put it into the models.
Yeah.
And that gets into data sharing as well. So unless we have,
Unless we have enough, exactly. But these technologies are the ones that are leading us in that direction. It's generate new hypotheses, generate new data, and that's how the field evolves, really. But I thought, AI is a device, is a technology, as you were saying.
Which is perhaps surprising to people. I don't know if you know that AI is a device if we're using it in medicine. We have to go through the regulation to make it a device. We might talk about that.
Yeah, and there's a huge debate that we can maybe touch on later in terms of which of these technologies should be regulated under what. But there's also some very physical, very tangible devices in this space, and you've spent many years developing one of them that you've hinted at earlier. Can you tell us about this device that you've
so
developed?
you might want, this was called Sponges to AI or something, this session, so I better show you where the idea of sponge comes from. So this is the latest generation of our device. So what we're interested in doing is detecting that condition, Barrett's esophagus, that I mentioned to you, which is the precursor for esophagus cancer. And currently, and historically, the way we've done it is by doing an endoscopy. Now, if I tell you the main risk factor for Barrett's esophagus is having heartburn. So, many of us experience heartburn. It's a very, very common symptom, especially if you're pregnant, but so the reason that most patients aren't diagnosed with Barrett's esophagus is because they don't get an endoscopy. Even in the US healthcare system, they don't get an endoscopy. So about 70 to 80% of Barrett's is undiagnosed. So we set about developing a device that could be used in a GP office setting, be super simple, that wouldn't require a camera, and the key thing it must do is collect cells, because the cells are the key to the understanding what's going on in a person's esophagus, because the cells tell us whether the Barrett's is there, and they'll also tell us whether the Barrett's is progressing towards cancer, because there's information about those cells that we can measure. And I was having a cup of coffee a long time ago now, about 2000, with my boss at the time in London, and we were talking about how endoscopy was not the answer, and we were joking about what we needed was a bottle brush for the esophagus. I actually made a kind of bottle brush. It looked a bit like a torture instrument. I made it in the old LMB workshop, and one of the chaps making it said, "You're not going to use this, are you?" Anyway, then I realized it needs to be something much simpler that you could swallow with a glass of water, that you didn't need someone to kind of, deploy down the right tube. So this is the capsule sponge, and it's evolved a bit over the years, but this is the latest version. So we can play the video in a minute, but this is going to deploy that capsule on the back of your tongue, and you just drink water with it. I'm not going to give you a real live demo. I've swallowed it quite a few times, and then the capsule will sit at the top of the stomach, and over just a few minutes it will dissolve, and within that capsule is a sponge which is compressed, and when the capsule dissolves, the sponge pops out, and then you simply withdraw it. Over a few seconds it will make your eyes water, but so quick you won't even hardly know it's done.
Shall we play the video?
And play the video, and then we can do the clever stuff, because then we send the sample off to the lab, which we'll come on to. So here it is, being deployed on the back of the tongue, the string's nicely bunched up to make it easy to swallow. You swallow the water, down goes the capsule to the top of the stomach, on goes the timer to wait till the capsule's dissolved, and then it's a nurse-led procedure, and the nurse pulls it out, and you'll be amazed how many cells we collect. So we collect 1 million plus, 1 million to 4 million cells on this sponge, on the surface and within the mesh. So we have plenty of material for the laboratory to work with. So then we shake the sponge in a liquid. It just goes to a regular lab in a preservative liquid. We shake the sponge and centrifuge the cells so we get a pellet of cells. And then we can analyze them. And this is the link, I guess, between the sponge and the AI in a way, because we've got a lot of cells. This is a very big sample. So, the pathologist is going to have to survey this sample and try and find the needle in the haystack. So we have some proteins which we've identified in Barts which help us know if it's there. So we can use an antibody to those proteins which stain brown. So if you click again. So there's a nice brown stain. So rather than the pathologist having to look at every single cell, they can be guided to where the brown staining is and evaluate that and say, do I think it's Barrett's? And then we actually use several different antibodies so they can evaluate it. But a machine learning AI is ideally suited for this kind of problem because it can immediately identify the areas which are brown and tell the pathologist whether they think there's nothing on this slide or there's something on this slide and which areas they should look at. And we can give a level of confidence to whether it's positive or negative. So it's not going to replace the pathologist. The regulation around that is very complicated, and the pathologists, good pathologists, are really good, and they spot very subtle things, but this can be a pathologist's AI assistant, is the idea. So that's one kind of device in AI, but I think you do something quite different, right? So you're more interested in, I think AI can be a bit like a Swiss Army knife or something. You can apply it in lots of different ways. So I think you've been using it to look at scans.
That's right. So images are the perfect type of data for AI because these algorithms are just really good at finding imaging patterns. Oh, there you go. So analyzing images, really for an AI algorithm, analyzing these pathology images is actually quite similar to analyzing a radiology scan, but the types of questions you can ask are very different. I don't know if some of you saw this piece of news. I think it was exactly a month ago when it was announced on a Monday. The government announced that the UK was going to lead what I think is now the largest trial for breast cancer screening. Rebecca, you were talking about breast cancer screening earlier. Supported by AI. They're going to recruit 700,000 women in this trial to demonstrate, hopefully, how AI can support the work that otherwise would be done by a radiologist. It was exactly the same type of situation, and we all know how stretched our workforce is. The predicted shortage of radiologists is 30% in just a couple of years in the UK. So anything we can do to support the work of our clinicians is, I think, welcome. And we'll talk later on, hopefully, a bit about the difference between automation and augmentation, which are the two main things that AI can do. But a lot of the work that is happening at the moment is around how we can make this work more efficient and hopefully more accurate. And that's what I've been focusing on. In terms of radiology, I've been looking at scans of the kidneys. So you're looking there at a slice of a CT scan, and the two structures that you see that are a bit kind of lit up on the sides are two kidneys. And the reason that we're looking at kidney cancer is that, well, we have no way to screen for kidney cancer, first of all. It's usually found incidentally. They were looking for something else, and they found the cancer. But as is the case with many other cancer types, the data shows that if you find it early, the chances that you will have a much better prognosis are much, much higher than if it's found when it's already symptomatic. And the opportunity that we had here was that there's already a screening program for lung cancer that is being deployed nationally. And the kidneys are not that far from the lungs. And so you could imagine taking a slightly larger scan, just including the kidneys. And the idea, this was actually a surgeon from Cambridge, Grant Stewart, who had the idea in the first place, and realized that sometimes they were seeing just the top of the kidneys, and they found some cancers in that way. And he thought, well, why don't we just extend this and see if we can find more of these? Now, it's a great idea in principle. The challenge is that the types of scans that you would get for the lungs are not exactly the types of scans that we would want to take to diagnose kidney cancer. So what you're looking at here, if hopefully you can see that arrow there, pointing at one of the two kidneys, there's this large grey blob that is basically the tumour. And when we do this type of imaging, it's called contrast-enhanced CT scan. The contrast enhancement is referring to the fact that you see that really clear, grey versus white type of contrast that helps you find the tumour. But this is not something we would do to everybody. You wouldn't go get a very high dose contrast-enhanced image just in case you've got cancer, because chances are you actually don't have cancer. And so the type of image that we get looks like this. Now, I've looked at these images many times with my students, and when we know the cancer is there, we're like, oh yeah, I see it, I swear I see it. And the truth is that it's really hard. So it's a good idea in principle, and radiologists are absolutely amazing. The things that they find in these scans, it's just unbelievable to me as a non-radiologist who's worked with them for many years. It's still really, really incredible. And I thought we could play like a little game, just to see. Yeah, I'm going to test everyone here just to see what you can find. So this is my test number 1. So this is an image that has not been enhanced by contrast. And I thought I would ask everyone to raise their hand if they think this is a kidney. Believe me, the kidneys, can look a bit. Yeah,
it's a bit of bump, isn't it?
Exactly. But is there something in there, do you think? Would you? I see a few hands who think that's a yes. Well, I think you have a budding career as radiologists, because there is something in there. When we look at the contrast-enhanced version of the image, we see really clearly that there is indeed a little bump. Now, if I show you this one.
Now you're making it harder.
This is number 2. Who thinks they see something? This is like one of those books that we had growing up. Can you see anything here? Is there a pattern? It's really, really hard. Most radiologists would struggle to find something here as well. And when you add the contrast, there really was a lesion in there. And this is why there's such a great opportunity in this type of challenge, because not only can we automate what the radiologist is doing, but we may also be able to find some patterns that are just not really visible to the human eye.
So could the AI find that?
So this one in particular, actually nobody was able to find. This was a really, really difficult one. But I'm going to show you, at least one other example. This is just a video of the trial that tested this idea. It was called the Yorkshire Kidney Screening Trial. It was an extension of the Leeds trial. This was led by Grant. And as you can see there, they're finding the kidneys as well. They're seeing the kidneys as well, not just the lung. And we used existing data, public data sets to train our algorithm, and we were able to validate it on the data from this trial. And what we found was that the AI framework was able to detect 100% of the cancers that were found in that data set. And what's really exciting to me now is that now we have this framework that we've trained, we know it works, we validated it on data from this trial. Now we can go to other cases and we can start to understand what we may have missed in the past. Yeah. And so I love this example because it really shows, it illustrates what you were saying earlier, Rebecca, about the evolution of these tumours, how they often evolved over years. Yeah. And we just weren't aware. So this is an example, and sorry, you can see the whole abdomen here, so it's a bit more complex. But I don't know if this is a pointer. But hopefully, can you see a red line? Can you see the red contour? That is highlighting the tumour in one of the kidneys. So this was someone who was diagnosed with that's why they got this scan. But there was someone who had imaging years ago for other reasons. And so we had included them in another study in which we were just looking back in time because we were interested in the early stages of cancer development. And so we found that they happened to have a non-contrast enhanced scan from 18 years earlier. And we looked at it and thought, well, can't see anything here. But when we ran the algorithm, I can't believe it. I'm not going to be, yes, no, you can see it. I was going to say, I won't be able to show you. Yes, it's there. Sorry, it's just that it's a zoomed out version of the image. So can you see that red circle in there? Yeah, so it's exactly the same lesion. I'm going to go back and forth, so you can see it is the same. It's the same case. It's just zoomed out for context. So the AI framework was able to find something there 18 years before it was actually diagnosed. So these are the types of things that we're starting to be able to do now, and to me it's really cool. Exciting. Yeah,
really, really exciting.
But obviously, I mean, the issue with these technologies. This is in the research setting, by the way. This is something we're doing in the institute, but it's still, a long way away from being used in the clinic, which is not the case for the sponge, because you've been working on it for a long time and you've done a lot of work with patients already in real-world settings. So I wonder if you could tell us a bit about the barriers that you found.
Yeah.
What the biggest barriers that you found.
Why does it take so long, right? Because I started thinking about this in 2000. It hasn't been my whole work for the last 25 years. We're doing other things, and it took a while till I kind of thought, actually, I think there's something in this, and I'm going to really work hard at it. But there are a lot of things you have to do when you're developing a device and when you're developing the lab tests. Of course, you want to know it's safe, and you have to prove that. You also need to know that it works. Actually, patients are much more enthusiastic often than clinicians, who are often very, very conservative and used to doing their endoscopy and don't necessarily want something else. And they're a bit skeptical about whether this sponge could do anything. So you need to generate the evidence. And if you're doing a trial about a new drug, then and it takes a long time to get a drug to market, but often the trials you do are quite small, very detailed trials, often starting with patients with advanced disease. If you're doing something like a device or a diagnostic, you need to do large-scale trials. You might start fairly small, but our first major trial was 500 patients. And then our last sort of third main trial was a randomized trial of 13,000 patients. And we're now doing some work for the NHS to help GPs, to help endoscopy waiting lists. But if we wanted this to be a national screening program like we have for bowel or breast, then we have to show not only that it's safe and that it works, because we showed in our last trial that we detect 10 times more cases of Barrett's than the GP does, so we were pretty pleased with that. But when I went to talk to the National Screening Committee, they said, well, that's very encouraging. You can find more Barrett's with your sponge, but I want to know if it really makes a difference. And by really makes a difference, you need to show me that it stops people dying from cancer of the esophagus. And it reduces what we call morbidity. It reduces side effects from chemotherapy and surgery because they have their cancer diagnosed earlier. Which is right and proper, right? But to do that, we're now doing a patient trial that's 120,000 people with heartburn and indigestion. And the follow-up will take 10 years. So I'll be finishing my career by the time I know. But the thing is, in the meantime, there's a lot, you can use this test in slightly different settings. So we've been using it for the NHS since COVID, and I think there might be another slide on this. So I got a call from the Scottish Government to say, can you help with our endoscopy waiting list during COVID? Because all endoscopy was going to be shut down, and we've heard you developed a little sponge test. Can we use it to triage people off endoscopy? And so that's what we started doing in COVID for Scotland and then England. And we've now done, our spin-out company's done 30,000 tests for the NHS. And Scotland are now using it routinely. So it may not be a national screening test, but you can start to use it to do some case finding, to triage people on endoscopy waiting lists and things like that. We're kind of getting there. And this is the mobile van that we're using for our heartburn health check, as it's called, which is our screening trial. And one of the other things that you have to really think about and work out, another challenge for early diagnosis and screening is, are people going to come and get the test? Right? Because unless you make it really easy and accessible and equitable, and the people who need it aren't going to get it, and your uptake then you won't make any difference. So it's all about getting people to take part. So how do we do this for our big screening trial, right? I've got to get 120,000 people into this trial. So first thing is to have a mobile van, so it'll go near to you in the Tesco car park. And maybe do the test first and then get a cup of tea rather than the other way around. But you've got to make it really easy. And And then the other thing is how you're going to invite them. So for our last trial, we got GPs to invite people. They went through their prescribing records, and if you were taking medicine for heartburn, they dropped you a line and said, hey, would you like to take part in this trial? Well, at the scale we're doing this, you can't really do that. So we thought, okay, we'll send a text message. Now, this is a long anecdote, but I'll make it very short. Basically, I thought it'd be easy to arrange to get a text message. We all got text messages about our COVID vaccines, and you probably get them now from your GP, and we found a company that can send text messages. But no, this is research. You're not allowed to send a text message unless you get permission from NHS Digitrials, which didn't exist when we designed the trial. So we applied to NHS Digitrials. And then I got the dummy text message, but it didn't have the NHS logo on. And I thought, well, that is going to be a fat lot of good, because if you get a text message inviting you for a heartburn health check with no NHS logo, everyone will delete it. So I had to apply to NHS branding and logos. And so we wrote a great thing. It sat in the Department of Health and somebody's desk for NHS branding and logos, and then nothing happened, and nothing happened, and nothing happened, and the vans were ready to go out, and I was despairing until someone had a secret way of getting me onto Wes Streeting's top of his pile. And then he said, of course, and signed it off, and off we went. So there we are. So now we're getting a text message. But these are the kind of things. And even now with our text message, the other reason about a text message is we want people who have over-the-counter medicine for their heartburn, not just the people that see the GP, because a lot of the people really at risk who have other risk factors and so on, they don't go to see their GP, they get the over-the-counter. So this means that anyone can get the text message, you don't have to have a prescription. But still, getting people to take part in these studies and screening in particular is really, really challenging. And that's something as a society and a public health system, we have to think about how we do that, because otherwise you can make the best tests in the world, but if you don't have the scan, or you don't have the sponge, or whatever it is, we're not going to find your disease earlier. So maybe it's easy for you in AI. Do you have any public health challenges?
Well, I mean, AI is all about challenges, really. I mean, one of the really critical things for AI is to involve the community and the public. And it's something that I'm really passionate about, and I'm lucky to work in an institute and with a lab where everyone is really committed to it. And realizing I didn't say that the work that I showed earlier was led by Bill McGow, a young PhD student in my lab, and it's usually these young scientists who are making a huge difference in the research that we do. But going back to the public engagement thing, I mean, it's just so critical, because unless we've got that engagement, most of these technologies will just never make a real difference. And I do a lot of work on renal cancer, but I'm also really passionate about gynecological cancers, women's cancers, which are a huge unmet need. They need a lot more research. Certainly, diseases like ovarian cancer are diagnosed very late, and we need to find ways to find them earlier and, well, to prevent that evolution. And Cambridge actually very recently hosted the first International Symposium for Women's Cancers, and it was just a few weeks ago, and I thought I would show a photo that we took at the end of that symposium, and I can see some people in the audience who are in that photo as well. And what is really special about this photo is that you can't tell by looking at it, but we've got an amazing combination of patients. We've got at least 6 or 7 patients in there. We've got clinicians, we've got researchers, we've got PIs, we've got younger researchers as well. All of us just working together. We spent 2 days talking about the main challenges for women's cancers. And it's this type of engagement that really helps us focus the research, and it's so important for AI. The only challenge is that it's sometimes difficult to explain the difference that it makes. Sure, it can help you guide the overall direction, and that's great. But I thought I would show you another example of a technology where patient engagement made a huge difference. And this is work that I do with a spin-out called 52 North.
It's another device.
And that's another device, as we know very well, because we have to spend loads of time talking about quality management systems and regulatory approvals and all that. And it's been really interesting for me to learn about all of that. But what's been really inspiring has been to see how co-creation really can take on a really tangible form when you're developing this type of device. So the reason that we developed Need to Check is that, again, an unmet need in cancer care. when patients are receiving treatment, chemotherapy and well, many others, they're at high risk of developing a complication called neutropenic sepsis. And basically what patients are typically told is if you feel unwell, if you have a fever, you need to call us, you need to go to A&E because you need to get urgent antibiotics. And this is hugely stressful. And in most cases, they actually didn't need to come in. So it's actually, it's another question. It's related to early diagnosis. Yes, I was just thinking about it. But it's for patients who are actually receiving treatment. And we've got this little device that it's portable, it's very cheap, and you can carry it with you so that if you do have symptoms that are concerning, you can take a quick finger prick blot sample and get 2 critical biomarkers, so 2 critical results. It's basically like a COVID test, but with 2 lines instead of 1, that will tell you if you really are at risk of developing this complication. Anyway, long story short, that's what the device looks like, and it seems pretty logical. There's two strips, and so there's a dial that you need to rotate to go from one strip to the other. And you would think that this is a straightforward decision to make. The truth is, it's not. We went through many, many iterations, and I've got a couple of examples here of the different devices that we considered. I personally really loved the ring design that you can see there, because I thought, oh, you could use it as a key ring, you could always have it with you. We had the 2 buttons that you would push. You would push button number 1 for one strip, button number 2 for the second strip. And we also had the question of, do we need an app? Do we not need an app? And what we did at every stage of development, every time we came up with a new idea, we went to our patient group and said, what do you think? And they had absolutely, I mean, to us, it was, I don't know, like, what should we do? To them, it was so clear. For example, some of them would tell us, well, I've got peripheral neuropathy. Basically means that it makes it really hard for me to handle really small objects. So if you give me those little buttons, or if you make me put my finger through that ring and put, it's just not going to happen. We said, oh, well, obviously, we just hadn't thought of that. And so it was a really, really beautiful example of how our communities, the public, the patients that we work with can make a really tangible difference in the research that we do. It's not AI in itself, but it's, as you say, it's a device. Yeah. It's a device.
And what did you end up with?
So we ended up with, when we did this test, we chose the dial that you can see in the bottom, on the bottom left, and then that dial evolved over time because we had to make more decisions. But yeah, it was a really good example of this. Now with AI, the thing that we always talk about is data. So we circle back to the data question. Yeah. And particularly if we're thinking about early cancer detection, prevention, we're talking about potentially looking at vast amounts of data early on in those journeys. So the question of data privacy is always asked. So I thought I could ask you as a clinician, what are the issues that you see around data privacy for these technologies?
Yeah, this is a big topic. It's challenging, isn't it? But data is absolutely the key. And I think many people would want to see improvements in healthcare. And so if that needs the data, that's a good thing. But of course, there are concerns about privacy. So one of the things we've been doing actually for our heartburn health check is working with Boots. Because Boots know a lot about who takes medication for heartburn, whether it's prescribed, whether that's bought over the counter. They can break it down for me by geographical area. The prescription ones, they can tell me quite a lot about the age and sex and things like that. The only thing they can't tell me is whether it's the granddaughter that bought it for grandma, et cetera, you know, that kind of thing. But they can tell us about the sales. And then with the loyalty cards with Boots, they can actually write to people who've signed up to the loyalty card, actually specify whether they're willing to be contacted for studies. And so pharmacists are actually starting to do quite a bit of research. And so through the loyalty scheme, we're then working with Boots to see if they could write to people who take these medications and say, would you be interested in taking part in this trial? There's another example with ovarian cancer. I think it was called the CLOCK study. And there they were interested in diagnosing ovary cancer earlier. And what they did was they looked at the shopping behavior, which they could get from people's loyalty cards, to see if there were any changes in the kind of medication that women started buying ahead of a diagnosis of ovary cancer. And what they found was that women started buying indigestion medication more ahead of their ovary cancer diagnosis. Now, obviously, there are a number of reasons you might, by indigestion, you might have a proper indigestion, right? But this is really interesting how that sort of data could start to, and the AI could probably, find the differences over time, the difference in shopping behavior that might be a trigger. So that would be really interesting and could be very helpful. But of course, it does require us to be willing to have our data used in that kind of a way.
This feels so close to our daily lives that I'm sure there will be some people in the audience thinking, well, it sounds like I could actually make a difference. What should I be thinking about? What's the next really exciting thing that's coming for screening or for early detection?
Lots of things, which is the cool thing. I mean, it's actually an exploding field. And some of it's really good and exciting, and some of it probably isn't very good, so we need to figure that out. And we need to make sure that it's being really rigorously tested. And we need people to take part in the studies so that we get the information, we know what's good, and we get the uptake to get the numbers and things. So I think that's where we can all play a part. So you may have heard things like the multi-cancer early detection blood test, so blood tests that can spot 50 different cancers, the NHS Gallery trial. There's been quite a lot of interesting debate about that, positive and negative. And then can we detect cancer on the breath? So some of you may be aware of Owlstone, another spin-out company from Cambridge. Fantastic, very inspiring story of Billy Boyle, whose wife died of colon cancer very young, and he was making devices to detect volatiles for defense purposes and thought maybe I can detect cancer in the breath. So there's a whole load of different sorts of devices as well as the AI that we're talking about. So I think it's an exploding field. There's something like 54 companies or something now making multi-cancer early detection tests. But they're not all brilliant, and they're not going to sort all our problems out tomorrow. So we need to be a bit patient before we sort of suddenly, start adopting things into our health system, which is why the National Screening Committee have the very big bars that they do, so that we properly evaluate who needs what test, when we use it, how we use it well. So, but we need, everyone to take part.
Yeah. And what do you think about the plans for the future of the NHS? I mean, we've been talking about the next 10 years for the NHS.
Well, the NHS have a new 10-year plan, and they're writing a new cancer plan. And I was very privileged actually to be in the Department of Health this week talking a bit about what should be in the cancer plan. And the good thing is that in the 10-year plan, they're thinking about things which are very dear to our heart in the Early Cancer Institute. They're thinking about prevention, so sickness to prevention, analog to digital, and hospital to community. Those are the kind of the three big messages. And I think that exactly chimes with what we're thinking about. How you do it is, I guess, another challenge. But I think, it's really good that our policymakers are thinking about these kind of things and talking to people like us. So I think that is really fantastic. So what about AI for the future? It's moving very, very fast. How much hope, how much hype? What do you think?
Yeah, so as you were saying earlier, it's such an exciting moment to be thinking about these things, because I do think that it will make a huge impact in the future. In terms of automation, as we were saying, it has a real potential to make the work of our pathologists, our radiologists, much easier. But there's also an opportunity to augment what we were doing before. And I always laugh because if I had been at this event a couple of years ago, I would have said, oh, but don't worry, an AI is nothing like a robot, because people always ask this. And the truth is, we're still not talking about robots, but the types of AI capabilities that we are developing these days are much closer to that type of really advanced decision support that you see in tools like ChatGPT. We are starting to think about what a medical co-pilot would look like. So it doesn't mean that we're not going to have doctors, right? Yeah. Because if there's something that is absolutely universal in every single, patient engagement forum, everything, everyone agrees that we want doctors. So they're staying there, but how can we maximize what they can do? And I see, at the pace at which AI is developing, we were discussing this the other day, we're talking about how we can set up a lab for research, for discovery, that has AI scientists that will just look at thousands of papers and give you ideas for what you should be doing next. Equally for a doctor, you can have a co-pilot that has an AI engine in it that says, well, have you thought about this? Maybe you want to test that. So it's this type of enhanced, augmented type of setup that I think we could realistically be starting to see in the next 10 years, which is
exciting.
Exciting. So I think that's the note that we need to end.
Yeah, I think it is. I think it is really exciting. Yeah. So I hope that's been interesting and some things to think about and talk about. So I think we may be entering a new era, I hope, where we can start to think about finding cancer earlier. Probably AI and devices are going to be part of it, and the public. So thank you very much, and we're really happy to answer your questions.
Thank you. And hopefully we do have time for some questions.
Yeah, we couldn't see the time, so that clock has been stuck on the same. I thought I was doing quite well, and then I realised the hand wasn't moving.
Thank you very much. The breast cancer enormous trial, that's going to be looking at mammograms? Okay, in the past, there must be millions and millions of mammograms that have been taken already.
Yes.
Are any of them stored and kept, and can that be used? Because, there'll be ones which are clear, and for the same people, they'll then have developed cancer, so there's perfect training AI.
That's a great question, and the answer is yes. I mean, normally those data are stored. Depending on the trial, it may be, or the setup, it may be stored for a number of years because there's obviously data regulation around it. But generally, yes, we store those data, and that's exactly how you train the algorithms. So I would say, in general, when you train an AI algorithm, you have to do it on data that has been taken and stored. So that those mammograms have indeed been used to train some of these frameworks. Now, the challenge is that when you have a medical device, as we were discussing earlier, when you have something that needs to be approved officially to be used in the clinic to help diagnose patients, you need to show that it also works prospectively, right? So you need to show that when you get new data and you apply your algorithm, you get the result that you want. And so that's why we also need those trials. So I would say it's a combination of both.
Yeah, we do that too. But to get it in the regulation into the clinic, you then have to train, test, and then independently test. And
yes, as you were saying, it's a long journey with lots of barriers. So it's a really great question. Thank you.
Yeah. And then we need to make sure we've got the right permissions for some of these data, because that makes it easier for us to do the trials on the retrospective stuff.
Yeah.
Lots of questions. Yeah.
So, with the endoscopy, was it Barts?
Yes.
Yeah. In terms of the Early Cancer Institute, will you also be bringing into that equation thyroid cancer? And the reason I say that is that some of the symptoms actually present as the same, but actually when they do the endoscopy, they miss the thyroid.
Yeah, we can't look at the thyroid through the endoscope.
Thyroid thing, because we actually had that with my mum, and we don't actually know whether that was one of the many things.
Interesting. That's interesting. I mean, so in the Early Cancer Institute, we're interested in a range of cancers. We're particularly focusing on the cancers with the poorest outcomes. And we've currently got 12 groups. Some of them are physicists, mathematicians, some of them are clinically trained. So thyroid isn't one we're currently focusing on. But, ultimately, of course, we want to cover as many as possible. But we also, I guess, have to think about where we can have the most impact as well. But
a community question as well. Do you have any ideas how you can work more with GPs? Because I'm hearing some, really fascinating hearing what both of you have said. But my gut feeling is saying that your thinking is so far ahead of the average GP, and that there might actually be people that know that they might be fitting the criteria of whatever you do, but whether they can actually get to see the GP or convince the GP to take that seriously. especially in the case where maybe they've got more than one thing going on.
Yeah, no, it's really tough for GPs, isn't it? It's easier for us sitting in, yeah.
Any thoughts of ways you could do that or
Yeah. So lots of thoughts about that. So yes, we do work with GPs. We are interested in accessibility, community. Some of it might be maybe thinking whether GP is overburdened, trying to look after sick people. Actually, we take some of this prevention stuff away from the GP and we do it in a mobile unit or in a pharmacy or something. And also how we make things more consistent and educate as well. So a test like this is very operator independent and it can be done in the community. And then there's a question about who is going to do it. So are you going to train every single GP, or are you going to do it in hubs, spokes and hubs kind of mechanisms? And what about vague symptoms, and when do you need an alert? So that's the kind of thing where there are increasingly these kind of AI agents, or some of them are simple decision trees, but GPs can use aids where they put in sets of symptoms or something about family history as well, and it'll tell them a threshold at which they should do something or not. So there's something called CAN risk, which has been developed in Cambridge using a huge amount of data, but it does exist. This is kind of risk prediction where you can fill in, a GP can fill in a simple set of questions and help them understand when they should be worried and when it's probably nothing. So CAN, C-A-N, it's CAN risk, CAN test, yeah.
Yeah. If I can add to that, there was an interesting paper published, I think it was last year or potentially 2023, that I think, no, 2024 definitely. And they had a survey, they launched a survey in the UK, and they sent it to GPs across the spectrum from, highly experienced to younger ones, to see who was using ChatGPT in their clinics. And it turns out that just over 20% were using ChatGPT already. So it illustrates kind of what you were saying. So I think there's a real appetite for these types of tools, even when it's not a regulated medical device, which is the case for ChatGPT. And so what we need to make sure is that all of this research is getting to the hands of the GPs and those who need it, as soon as we can. And we're doing a lot of work with policymakers. Rebecca, you do a lot of work on this with the Centre for Science and Policy at CSAP here in Cambridge. And this is definitely a top priority for policymakers at the moment. And we just need to work as a team.
Yeah.
Sorry. Thank you very much. I enjoyed the talk. I'm a great believer in AI, and I think it's going to revolutionise not just medicine, but everything. However, I have got a minor concern. It's that if you have a little box and you stick a question in it, you believe the answer. As we all know, it's due to likelihood ratios. Any test, or cancer test, or anything with imaging is likelihood ratios. Those that have got the disease, i.e. it's sensitive, divided by and minus those that don't have the disease. So it's specific. And my concern is, and particularly, for example, is persuading a surgeon on that previous cancer of 18 years ago, is he really going to take that out? And you think, I just wonder what your thoughts were. The other thing while I'm here is that the NHS should be ideally placed. And please, for people here, if you go to the app on your NHS app, you can volunteer for research. And okay, I'm an old boy, so I need to volunteer because you never know what might be around the corner. The other thing I would suggest is that that case, the likelihood ratio, it was actually tested in the law because one of my colleagues, who is a paediatric cardiologist, didn't warn mother and the father that there was a risk of death. And he said, but the risk is 1 in 10,000, which isn't, my view, isn't it? It isn't worth. You shouldn't frighten the patient. And the judge said, people buy lottery tickets. The chances of being successful are far more remote than 1 in 10,000. And that's the problem I have, really, is I'm a little bit concerned that people believe everything they get out. And it's with everything, whether you're talking to your doctor or anybody else. You should have a degree of suspicion, perhaps.
I mean, there's loads in that comment and that question. I mean, this is one of the biggest challenges for screening in general. And we were talking about how you were saying, yes, we need to go to prevention, but we're going to have to learn how to deal with the amount of data and the amount of suspicious cases we're going to find when we use these technologies, some of them based on AI, some of them not. I mean, in these trials, even when it's a person looking at it, sometimes they're just not sure. And so, in part, this is just a learning process. I mean, Rebecca, I mean, as a clinician, this is what you see every day. For me, as an AI developer, there's two really important points. One is we have to develop AI with an objective in mind. So there's a lot of people out there who develop, who are pushing the field forward and developing AI, quote unquote, for the sake of it. And that's when you can enter some of those really dangerous areas of claiming that something is very sensitive and very specific, and it could be great for early detection, but if you're not really testing it in the population that you really care about, if you're not testing it in a sample where you've got thousands of images, but only 2 have cancer, you won't really know the errors that you're making. So it's really important that we develop AI in an interdisciplinary manner, working with clinicians who tell us these are exactly the questions that we need to ask, and this is what you need to evaluate. And the next thing for me as a computational scientist is that, and that's again a point that you made, these tools are not going to be used in isolation, or at least that's the current consensus. We should never be using this in isolation. And it's very important that when we test them with that person in the loop. And there's a really fascinating behavioral science challenge around this, because when you see something suggested to you, you're likely to behave in a different way than if you hadn't had any prior information. But there are behavioral scientists looking at these questions. So it is a challenge, but
at the end of the day, someone's going to have to make the decision.
Exactly. Yeah.
And in healthcare, that's going to be a doctor. So
yeah.
They will use, they're used to use that as a tool, but they're also using their experience and their education, hopefully, to make the right decision. And we won't get it right 100% of the time. But hopefully some of these tools will help it be more consistent and right more of the time. I think that's, yeah.
Thank you very much for the talk. I'm particularly interested in the early detection stuff. If it's 10 years before, because as we know, the earlier detect, the better the treatment, and the less invasive it is. The problem with that is, of course, then, you don't have any symptoms. It's very hard to see. So you really have to go into the screening regime. But if you want to do screening here and you don't have any indicators that it's there, you really have to do mass screening. Then we're looking at scale up. We're looking at cost. Then it becomes an engineering problem. The other thing I liked about the blood test that you mentioned is I don't want to develop a device for every single type of cancer. If I can do a blood or urine test and screen immediately for 50 plus types of cancer, the relatively high rate of success. What are the chances of developing this further, and especially making it cheap? Because we've seen during COVID, for example, the lab capacity in this country was quite low, and they really struggled with that. So do we build up industrial scale capabilities for testing quickly, cheaply? The other thing is it's non-invasive, right? If you have a blood test, well, as a blood donor, it's a small invasion, but it's a quite simple, and it's very low risk. Or urine sample is even easier to have that. So what are the chances of really going in that direction, and thereby making cancer detection much easier, much faster, and thereby getting to treatment much earlier?
I mean, all the points you make are fantastic points. So it's absolutely about ease of access, ability to simple tests, ability to scale up, whether the economics stack up. And that, of course, is the hope of the multi-cancer early detection test, is that it is simple enough. You can scale it up. And if you find these cancers early, the health economics gets quite complicated, but if you start thinking about the cost it would have cost you to treat later on, then these tests all cost money, but you may save money in the long term. So I think this is the promise and what people are excited about. But it's already clear that for some cancers, these tests currently don't work very well. But it's changing, right? The technologies are improving. The amount of information we have are improving. But some of them is about the limit of detection, potentially. So some of these cancers, when they're very early stage, may just not really shed into the blood. And breast cancer, for example, seems to be, from the current evidence, quite difficult to detect in a blood test. But we have a very good test for breast. So maybe that's fine. So you may not necessarily be able to solve everything with a blood test. You may still need some kind of combination. The other question is, do you want to test everyone for everything? Even if it's all available on the blood test, you don't have to necessarily analyze everything, because your false positives are very, very important, right? And so you could already kind of threshold your risk based on other factors. Or if you know your risk is really high for one particular thing, then you might want to really go and look for that very particularly, even if it is a bit more invasive and it is one cancer at a time. So these things get quite nuanced and quite complicated, but I think the points you raise are very, very, well made.
What about multi-stage screening?
Yes, doing it more than once. Doing it more than once. So this is something I'm very interested in. So often, in our medical care in general is based on what do I know today and all the tests from this point in time. We don't use the serial information, right? And we get an awful lot from the delta. So it may be very, you may not detect it from that one single thing, but if you had 3 data points, then it may suddenly become very obvious and a lot easier. So I think that is the other exciting thing. We should, be monitoring things over our lives. And we don't necessarily, more is not always, actually I'm not the best attender at screening and things. But because what we want to do is to live healthier and, and to enjoy our lives, right? You don't want to be running to the doctor every 2 minutes, and you don't want to have lots of interventions that you might not need for something that might never cause you a problem. So one of the programs we've been doing is people at very high risk of stomach cancer because they've got a genetic inherited mutation. We've been doing work to try and save them having their stomach removed, because we know that actually there's a range of risk within those families. So, it's not just about lots of testing and lots of treatments. It's working out when we can reassure people and let them off the hook, and when actually we can do something useful and get there earlier. So it is quite complicated, but I think there is definitely, that's the direction of travel.
Amazing to see so many questions. Well, just because we have another talk, so just 2 more quick questions. Are you happy to take 2 more questions? So I know that gentleman over there was waiting for a while.
I think it was kind of answered before, which was really how good's your AI at telling you don't have cancer, and what kind of havoc does that reach on the population? But I think that's probably been covered by some of the previous questions.
Yeah, I mean, it's absolutely, you need to test, in our case, on data from a screening trial to know what it is. We haven't published this yet, it's under review, so I'm not going to spoil the results, but it's very good.
Well, thank you very much for a most interesting and well-presented talk, and it's clear the audience loved it. Could I ask a possibly stupid question, but I'm not a doctor or anywhere near it. Do animals get cancer? Could we learn anything from that?
Yep, some animals do and some animals don't. So we can potentially learn something from that. So naked mole rats, for example, don't get cancer. And you might think that size scales with cancer because you've got more tissues, but that's not necessarily the case. So, yeah, I don't do that kind of research, but there are definitely people finding out what we can learn.
It's a great idea.
I thought that was really loud. I thought that's a fantastic talk, Rebecca and Maria. Maria, you mentioned the importance of patient and public involvement in your segment. So this isn't a question. This is actually just a bit of a plug for the 13 patient and public involvement groups at the Cancer Research UK Cambridge Centre. If anyone here is interested in helping us to shape and design our research, if you pop us an email at involvement@cancer.cam.ac.uk, we'll put you in touch with the right patient group.
Thank you, Rhys.
Brilliant. Thank you, Rhys.
One last question, if that's okay.
This is a slight follow-up from the gentleman over there. I'd be particularly interested in getting involved with the breast cancer research that was advertised here to do with AI and breast cancer. And it's a slightly personal story, because just over 30 years ago, I was diagnosed with breast cancer. The very early stages of breast cancer. As it happened, I went for a medical. They said, come back in 2 years if you want a smear and another mammogram, which I did, which showed various cell changes in one of my breasts, from not quite knowing what was happening to precancerous cells. I had a biopsy, some treatment, and then I went back the following year for the follow-up mammogram, which showed a cluster of more little white dots. Weren't sure what it was. Maybe it was dead matter left over in the radiotherapy and it had done its job, or maybe not. Bearing in mind this was 30 years ago, just over 30 years ago, I went for the mastectomy because it was not my best friend. And as far as I was concerned, I'd already decided if it thinks about doing something it shouldn't do, it can go. As a result of that, I'm having I go for a mammogram initially every year, but then was suggested I went for 2 years because I had a cyst, a water-filled cyst, and I was told it would be a good idea to go for it every year, which I do religiously. So I'd be really interested in getting involved in, because I'm here today thanks to that early diagnosis, because I was then told, and I was signed off eventually, that the consultant would have given me 3 to 5 years. So I'm very keen to get involved in some kind of research, and needless to say, my daughters and grandchildren know all about how to sort yourself, how to look after yourself in that respect, which is really important too. So I'll be really interested to know how to get involved in more research from that, particularly the breast cancer point of view.
Well, thank you for sharing your story, and wonderful testament to early diagnosis. That's a very good note to end on, that it can work. And do drop us a line at the Early Cancer Institute. You'll find our email on the website, and we'll put you in touch with the right person. Thank you for your interest in research, and anyone else that's interested in research. You know, the new hospital, the hope is that we can involve relatives of our patients in research as well. So lots of opportunities. So thank you. I think we're out of time, but thank you all very, very much again for your fantastic questions. Thank you, Reese. Sure.
Once you've done the spotters, I used to work in pathology labs.
Right, yes.
Is it formalin fixed? You get the little pellets?
Yes.
Formalin fixed,
We do.
section.
Yes.
My medical science.
Because then we do our immunochemistry. Yeah.
Yes. I don't think they're turned on. I don't know. There was my voice booming around the.
Actually, the immuno works really well.
Yeah, I mean, I saw the little bracket. I've seen that for 7 years. That's lovely.
Yeah, thank you.
Hi, I work for a company called Allele Health. We're owned by another company called Origin Sciences. So I think you might have worked with before.
Yes.
They use a balloon to collect a rectal sample.
Yeah.
We did the same to collect a vaginal sample. Worked really well. I'm really interested with. We're focused on endometrial and ovarian cancer in our next study. But we think the device is quite cool, and we really want to cast our research net as wide as possible. Is it worth getting in touch with Early Cancer Institute to understand a bit more about your research and gynecological
Yeah, I can put you up in touch with someone to talk about.
Yeah, that would be really interesting.
Yeah, we're having a bit of a focus on endometrial actually coming up. Have you met Philippe?
I haven't.
I've forgotten his surname. Anyway, he's based mainly in London now, but he might be a good person. I'll put you in touch if you drop me a line.
Yeah, that would be really great. Where would I find your email address?
You can easily find it on the website.
Amazing.
Yeah.
Thank you so
All
much.
right, thanks for coming. Thanks.
May I ask how likely is it that the Galleri test will